Okay, so today we're going to do something a little different. We're not talking about a brand new gadget or some crazy scientific breakthrough. No, we're going to tell the story of something that teaches those things, a textbook. And trust me, this is not just any old book. This is a story about survival, about how you stay relevant when the world is changing at light speed. It's really a story about knowledge itself.
This right here is electronic devices and circuit theory. Now, if you studied electrical engineering anytime in the last, 50 years, I'm willing to bet you've had a few late nights with this book. It first came out way back in 1972, and it's become this absolute rite of passage in the field. It's a classic for a reason. And that kind of leads us to the big question, right? Think about 1972 for a second. We've gone from computers that filled entire rooms to computers that fit in our pockets. The entire technological universe has changed. So how on earth does a textbook born back then avoid becoming a total fossil? Well, that's the mystery we're going to unravel.
So first, let's just get a feel for the absolutely incredible journey this book has been on. You know, when that first edition hit the shelves, the vacuum tube was still a big deal. Since then, this book has lived through the rise of the transistor, the personal computer boom of the 80s, the entire digital revolution. And now, in its 11th edition, it's talking about things like nanotechnology. It has literally watched whole technologies be born, grow up, and then just fade into obscurity. So you can see the main battle in our story, right? It's this one book up against the relentless, unforgiving pace of technology just making things obsolete. And the scale of the change here is just staggering. The authors themselves point out that the very first edition was almost all about vacuum tubes. And the current edition, it's a completely different world. It's all about semiconductor devices, with chapters on solar cells, LEDs, and even stuff that sounds like science fiction, like carbon nanotubes. This quote from the authors really says it all. The main technology of the first edition, the thing the book was all about, has literally vanished from the table of contents. It's not just updated, it's gone. That's like reading a history book where the entire Roman Empire chapter was just deleted and replaced with a chapter on the space race. That's the level of change we're talking about here. But here's where the story gets really cool. Just as those old vacuum tubes were on their way out, these new things called field effect transistors, or FETs, were coming in. And here's the twist. It turned out that a lot of the math, the models, the ways of analyzing the old tubes could be applied directly to these brand new devices. And that just shows you something so important. Even when the hardware dies, the theory behind it can live on. So how do they do it? How do the authors keep up with all this change? Well, it's not magic. It's a really smart, continuous process. I mean, just think about it for a second. If it was your job to update a book like this, where would you even start? What's the first thing you do? Well, according to the authors, it all comes down to this four-part feedback loop. It starts with the students, right? The people who are actually in the trenches, using the book, getting confused by certain parts. Then you get input from professors who are teaching it. After that, the publisher brings in their own experts to review it. And finally, the authors themselves just reread their own work after a few years and find things they want to make better. And this quote right here is the key. They say that above everything else, it's the real-world classroom experience that shows them what needs to change. It proves that the book isn't some static thing sitting on a shelf. It's a living document, constantly being shaped by the very people it's trying to teach. All right, so let's take a look at what all that feedback actually results in. The 11th edition isn't just the 10th edition with a new cover, it's been seriously rebuilt in some really important ways. The list of updates in the preface is huge. I mean, they've updated all the software sections to match the tools being used in the industry right now. They've added brand new material on emerging tech, and they've even added photos and bios of the pioneers of electronics to give the theories some human context. It's a total overhaul. And just to put one number on it, they added over 100 new problems for students to solve. Now think about that. That's not just about adding new information. That's a serious commitment to making sure students can apply the concepts to turn them from passive readers into active problem solvers. That is a massive amount of work for a new edition. Which brings us all the way back to that first big question. After all this, how has this one book managed to survive for half a century? Because the answer isn't just, oh, they updated a lot. There's something deeper going on here, something fundamental to the book's DNA that gives it this incredible staying power. The secret is actually hidden right there in the title, Electronic Devices and Circuit Theory. See, the devices, The vacuum tubes, the transistors, the nanotubes, they come and go. They're temporary. But the theory, the basic rules of physics and math that describe how electrons move through a circuit, that doesn't change. That is permanent.
And that's really the big idea here. This book has lasted so long because it's built on a foundation of timeless principles. It doesn't just teach you how to use the latest component, it teaches you how to think about electronics. That's why the math for old vacuum tubes could be reused for new transistors. The language of electronics stayed the same, even when the vocabulary changed.
And that really leaves us with a final thought, doesn't it? In our world where we're always being pushed to learn the new software, the new platform, the new framework, the story of this one book makes you stop and ask a pretty important question. What are we learning that's just temporary, and what are we learning that's truly going to last?